All right, so welcome to this iteration of the modeling series. I'd like to introduce Prabhat from Lawrence Berkeley National Lab, who sits at this intersection between scientific computing and machine learning. That's, it got born about 10 years ago, I think, no older than that. And he'll tell us about how the work there is going. Go ahead.
Cool. All right. Thanks, Greg. Thanks for having me here. Let me just share my screen. Still make sure that everything comes up okay. All right. Is that working, Greg?
Yep.
All right. Perfect. Great. All right. So again, thanks for having me over. I understand it's a little early for computer scientists, but hopefully, you all can see the recording later on, just in case you're not here today. So what I thought I would do today is to really give a perspective on how modeling has evolved in science, these are just some personal thoughts that I have, and hopefully, you'll get to learn something new. So this is the outline to the talk. Not all of you may be familiar with the Department of Energy where I work. I work at DOE's Berkeley Lab campus. I'm going to just briefly introduce you to what Berkeley Lab is all about, and in particular in Berkeley Lab, I work at a supercomputing center called NERSC. So I'll just briefly again introduce you to NERSC. Then we'll get to the meat of the talk, which is how computational modeling has evolved over time, how data-intensive science is sort of the up-and-coming new thing in science. It's been for the last decade or so. And then finally, of course, how deep learning is rising in science, and then how deep learning can be applied to both computational modeling and data analytics. Now, as we go ahead and try to do that marriage, I guess, apply deep learning to traditional computational modeling and data analytics, there are a number of interesting challenges that arise at the interface. So I'm going to comment on that. And really, I think the reason maybe I'm giving this talk here at this venue is because while folks like yourselves at Google have really pushed hard on deep learning, we've been pushing quite hard on science for the last 40 years. And really, I think when you try to combine the two, so deep learning to science at an HPC facility, there are some unique challenges that arise. And I think there are a lot of opportunities to collaborate and work together on that. So at least I want to make you all aware of what those challenges might be. All right, so again, just to orient you geographically a little bit, if you drive 45 minutes north of Mountain View, you're gonna approach the East Bay. So when you hit the city of Berkeley, you'll see the beautiful East Hills on the right side. So this is roughly looking in the northeast direction on the top. And the UC Berkeley Stadium is off to the football stadium is off to the bottom right. And essentially, this campus is where Berkeley Lab is. So we are nestled in the East Bay Hills, right next to the UC Berkeley campus. It's really quite a great location to be at. This is again a view looking out to the west, so the Golden Gate Bridge and the San Francisco skyline is out there in the distance. And this is the Berkeley Lab campus in the foreground. And again, UC Berkeley, so some of you might know the statistics, math department, the Campanile, and so on is right next door. Berkeley Lab is known for science. Again, we do pride ourselves in being the premier research lab, basic research lab in science. So it's known for its legacy of many Nobel Prizes, mostly won in physics and chemistry, many medals of science, and then there are several National Academy members. This person on the top right is Alexander Shorin, who is responsible for many advances in solving partial differential equations. And then this person on the top left is Saul Perlmutter, who won the Nobel Prize in Physics recently, which was, and his discovery and his colleagues' discovery was around determining how supernovas can be used as standard candles, which can then be in turn used to measure distances in the universe. And they essentially discovered that the universe is expanding at an accelerating rate. So again, a rich legacy of science. I'm not going to have time to cover everything that Berkeley Lab does. But really, I think I'll be focusing on this building, which is our home, NERSC, the National Energy Research Scientific Computing Center. Acronyms are a mouthful in the federal government, I guess. But anyways, this building houses the staff, but then also the machines that power a lot of our compute. So we have a tradition of naming machines after famous scientists. Gertie Corey is, in this case, the Nobel laureate in chemistry, whose machine is named after. This is our flagship machine at this point in time. So just to give you a sense for scale, we can talk openly about numbers and scales of machines at NERSC. So this machine, this supercomputer, which is provided by Cray, has about 2,000 Intel Haswell CPUs, and then also 9,600 Intel Knights Landing nodes. So that's a typical scale for a contemporary HPC machine at this point in time. And again, apart from just doing compute, being able to store data is important. So we do have reasonable file systems. So right now we have a 30 petabyte Lustre file system that's connected to this machine. And then the interconnect is really where a lot of the magic is on any HPC machine. So Cray has a proprietary interconnect called Aries, which can support reasonably high bandwidth and with low latency. So that's the interconnect that we use. So for the last 3 years or so, all of our simulations, all of our data analysis jobs have been running on this style of a machine. Going forward, so later this year and earlier next year, we're going to be deploying our next system called Perlmutter. So that's named after the Nobel laureate. So if you, by the way, so if you win the Nobel Prize in the Berkeley lab ecosystem, you get a road named after you. You get a free parking spot at the UC Berkeley campus, and then sometimes you get machines named after you as well. So in this case, we felt that Saul Perlmutter was really worthy and extremely friendly. You can see him here with his cohort of grad students and postdocs. So anyway, so he's been really quite a legend, I guess, in our community, and we are naming our system after him. But just onto the technical specs, Perlmutter has more than 3,000 AMD Milan CPUs, and then it's going to have more than 6,000 ampere GPU nodes. So each node will actually have 4 amperes, and then the AMD Milan CPUs as well. So this notion of heterogeneity is finally hitting NERSC and other supercomputing centers now, in that you're not going to see CPU-only systems. You're going to see hybrid CPU-only, GPU partitions, and then some custom accelerator nodes. That's starting to happen. Another important trend for us really is that the file systems aren't keeping up. So we are exploring a range of storage substrates to accommodate data-intensive workloads. And again, now, while Lustre will be our file system, it's going to be based on all flash. So it's not going to be spinning disk anymore. So that's an interesting trend that's also happening. All right. So hopefully you have a sense for what our machines look like. Again, this is a very high-level view of things, but just diving in a little bit on the science side, just to give you a sense of the breadth of what we do. So we, as a center, have been supporting simulation workloads for the last 40 years. So that's really a long time. So Greg, comes from Livermore, and there was a point in time when NERSC was actually a part of Livermore, and then it broke off as an open science facility. And again, for the last 40 years, NERSC has been supporting primarily simulation workloads. So this is a visual gallery of various domain sciences and so on. But just to call out a few domains, you might be interested in modeling the Earth system. So you might be interested in simulating the atmosphere, land processes, ocean. There might be other biological systems within a part of the Earth system that you might be interested in simulating. You might be interested in simulating essentially the entire universe. Of course, there are many components to the universe. You might be interested in the cosmic microwave background. You might be interested in stellar explosions and so on. You might be interested in high energy physics or nuclear physics, so essentially what comprises a molecule or an atom. You might be interested in the macroscopic properties of molecules, running chemistry simulations, running geophysics simulations, subsurface simulations. You might be interested in creating, a tokamak, a fusion device that can produce energy in a different way. So really, it's a very broad gamut of use cases. We have, at this point in time, about 7,000 users, 800 different projects. Truly, we have users from every state in the US, but then also other countries around the world. So it really is an open science facility. Now, on the computer science side, which is the middle panel up here, the DOE, I would say, in the US has been responsible for the terascale mission, the petascale mission, and now the exascale mission. So really charging on getting all of these large-scale HPC systems to run and operate and be productive is a mission that the DOE owns. So that's been a big common theme. And again, systems at Livermore, systems at Berkeley Labs, systems in Oak Ridge National Lab, Argonne National Lab, so on and so forth, have really led the charge in that regard. Many of you might be from universities, and when you were students, you might have accessed supercomputing centers at your university. So the NSF also has a presence in the HPC1. But really, I think there is a very important component to scientific computing, which is around modeling. So again, if you care about simulating all of this phenomena that you're seeing, all of the complex natural phenomena that you're seeing on the screen in front of you, then you really need to be able to think systematically about how you proceed with computational modeling. So a lot of the intellectual energy is really in the field of applied mathematics in the DOE. And then, once you've created a computational model, how do you run it on a big machine? So that's also a unique challenge that comes up in the DOE. All right, so hopefully, you have a sense for the breadth of, the kinds of problems that we work on. So I want to now maybe just chat about computational modeling. Again, this is something that we've done well, hopefully, for the last 40 years. And just to draw a caricature of how one proceeds with computational modeling, we're going to be comparing this flowchart, I guess, to what we do in deep learning later on in the talk. But again, this might be obvious to many of you, but just to walk through this cycle at least once. There is probably a natural phenomenon you want to study. So one of the first things that you do is to talk to physicists and the domain scientists and figure out what the underlying governing laws are. So it might be a partial differential equation, it might be a conservation law, so on and so forth. Then you talk to the applied mathematicians and you figure out how you might go about discretizing the spatial domain or the temporal domain of interest. So you might choose to use a structured grid for the discretization and unstructured grid. You might choose to use particles. You might choose to use an adaptive mesh refinement scheme that varies the discretization over time. Then essentially you plug in a solver. So again, having talked to applied mathematicians over a long period of time, there is a suite of many solvers that you can choose from that all have different characteristics. Thankfully, many of these solvers actually have analytical proofs. So you can be assured that once you've chosen a certain solver and a certain discretization scheme, your solver will actually converge to hopefully the right thing. And even if it, even if it's off, you have a sense for the kinds of subgrid scale phenomena you're not going to be able to resolve. So typically, these solvers have been analyzed. Their properties, their theoretical properties are well studied. And once you've chosen a certain solver, then you actually go ahead and implement it. Of course, you don't implement things from scratch. There is a code base of for many solvers that have been developed over the years. But nevertheless, once you've made those important decisions, then you can either pick a code base or you can implement something. And when Stefan was giving a talk at Berkeley Lab the other day, there are emerging code bases in new Python-like languages that you can also, of course, develop. Typically, these phenomena are complex. There might be a large spatial domain or a long temporal duration that you want to simulate the system in. So this issue of scaling, how do you get first the code to run well on a certain compute element? It might be a CPU, a GPU, a TPU, or some other accelerator. But then also, how do you get it to scale well across many such compute elements is a challenge. And then really that's where a lot of the high-performance computing folks have been focusing their efforts in collaboration, of course, with the applied mathematicians. Now, once your code is ready, it's running, it's scaling on a big machine, then, of course, you can use it to predict phenomena, or you can use it first to validate how well your code is doing compared to some observation product. So, for example, if you're trying to simulate the Earth system, then you may choose to discretize the Navier-Stokes equations. You might plug in a certain finite element or finite volume solver. Then you might choose to run out the climate system for a period of a year, initializing it appropriately. And then you may choose to compare the output of that solver with some observation data and see if you've done a good job. If you validated your model, you trust what it does, then you may choose to plug in a different scenario, have it run out or make some predictions in a future scenario. In the case of the climate system, what's going to happen to the Earth by the end of 2100. And then those are some numbers or some predictions you may choose to use. Now, of course, there's a notion of error everywhere. There are things that you're not going to get right. There are aspects of the natural system you're not going to be able to model. So this is really a loop in that you try to improve your understanding of the natural system based on the predictions introduce some more laws or model some more laws and so on and so forth. So this is really how computational modeling has proceeded over the last 40 or more years at a place like at an HPC center like NERSC. Now, there are certainly limitations. Applied mathematics is still a very active area of research. This is my list. By no means is it extensive, or by no means is it exhaustive, I guess. So if you talk to a different applied mathematician, you're going to get different take. But from my perspective, I guess sitting at NERSC, there are classes of limitations that computational models have. Again, despite the 40 years of progress that we have, it is still the case that some natural systems are just very, very hard to model. So if you look at the atmosphere, there are processes at the scale of an atom, at a molecule, processes at the scale of meters, spatial scales of meters or tens of meters, subgrid scale processes that might be at the scale of 25 by 25 kilometer box, which are just not going to be able to be processed once you've fixed your grid. So again, natural phenomena are typically multi-scale and multi-physics. And despite all the compute power that we have in the world, we just may not be able to do a good job at resolving all of the scales and all of the physics and chemistry. Often, the phenomena that you're studying might be chaotic, it might be nonlinear, it might be a dynamical system, and such systems have limited predictability. So really, it doesn't matter how well you initialize your system, how well you specify the boundary conditions, you're not going to be able to predict more than a certain amount in time. So again, if you go back to weather forecast, for example, problem that Google is interested in, I think, you never really hear of weather forecasts beyond 14 days. Typically the weather forecasts are done for a week or 3 or 5 days. That's essentially because the system is chaotic. So that just has to do with the nature of the problem, the nature of the science.
Yes. Let me separate two things. Maybe the second one is going to cover this. So there's two. If the underlying physics is chaotic, if you had it perfectly, your lack of knowledge of the initial conditions, which is always going to have an error, is going to doom you. The other one is that errors amplify through your approximation, either of the physical laws or of the numerical scheme. So I guess in these things, which one dominates, or both?
So both do. In some ways. There are going to be, of course, natural processes you're not going to be able to capture. And again, depending on what you're interested in studying. So for example, when we are interested in how the climate system might evolve, might change by the end of the century, so we're looking at a 100-year prediction, then certainly the lack of modeling aspects of the system, such as lakes or what the humans are going to be doing, what kinds of emissions they're going to be, those uncertainties will dominate, in decadal time frames. So 20, 30, 40 years from now, that's going to dominate. And then certainly, aspects of uncertainty attributed to initial conditions and so on, might dominate initially. So again, both things dominate. It depends on, what is the property of interest that you really care about. So as Greg just mentioned, our knowledge of the world is imperfect. So there are going to be conditions that these computational models require around the initial condition of the system, the boundary conditions, and it's always going to be imperfect. Not only that, but as all of you are programmers, you know that your programs typically have parameters. So do PD solvers, so do computational models, and things that your computational model is not going to be able to resolve. So things that might happen within a box. So that is what we call subgrid scale parameterization. Those are again things that are represented by numbers, and typically heuristics are used to determine what those numbers might be. So those are not laws of nature. Those are empirical observations, or at best, and heuristics at worst. Those are also limitations that many of these models have, and we are repeatedly running into those now. Uncertainty quantification is an overarching challenge. I think just as what Greg mentioned, because of this, there are different sources of uncertainty, and how do those uncertainties propagate over time? Do they dominate in the end, so on and so forth? That is an important overarching challenge, I would say, in computational modeling. So that's sort of one set of issues. Then, again, despite having access to all of the HPC resources we have in the world, Sometimes the space of configurations you need to explore is just way too large. So think of the space of molecules that are possible for the climate system. Think of all of the initial conditions and boundary conditions, the space of parameters you might have. So really, there's just no way for you to be able to enumerate explicitly all of the configurations and run out these 100-year simulations. It's just not happening. On the HPC side, again, despite all of the progress in applied mathematics and computational modeling and performance and scaling, I would say that many of the applications are now running into challenges wherein, while I think we've explored weak scaling, wherein you proportionally scale up the size of the domain as you throw more compute power at it, many of the applications are now running into strong scaling bottlenecks. For a climate system, you might have a coupled model, so you might be coupling an atmosphere to land to ocean, and all of these might be different code bases. So being able to load balance them is turning out to be now a major challenge, and we're just not able to get these coupled models to run any faster, unfortunately, anymore. Now, also, I mentioned heterogeneity in the HPC center, in that you're starting to see different compute elements with different trade-offs. And again, how do you get complex simulation codes to exploit heterogeneity? So if on a node, if you have 2 CPUs and 6 GPUs, how do you get some part of your compute to run on maybe the accelerator and then some to run on the GPU? That is going to be, that is a challenge already. So again, there are computer scientists who are starting to look at this. I think some of the work that Stefan was pointing out is headed in that direction. You can take off your compute element, obviously, as a TPU. So there is a nice problem there for the computer science folks for sure. So that's sort of one set of challenges that I think we now collectively face in the computational modeling community. I do want to call out a different trend, which is the rise of data intensive science. So in parallel to these developments that have been happening for 40 years, we now, of course, see many domain sciences purely driven by data. So in many cases, there may not be a computational model, but you're just seeing such a vast amount of data coming in that to a first order, what we care about are cleaning up the data, making sense of patterns in the data, finding anomalies in the data, and so on. Once in a while, you might have a computational model to compare things to, but many of these domains are now driven purely by data. So just to give you a visual sense for what these domains are, modern day astronomy is done by robotic telescopes. So on the left is an instrument called DESI, the Dark Energy Spectroscopic Instrument. So this is a robotic telescope that, once you open up the aperture for this instrument will sweep the nighttime sky. These telescopes used to be optical historically, but now we are seeing many of the telescopes being augmented by spectroscopic probes. So these are optical fiber cables, and you can programmatically control them to point to a specific galaxy or a specific star. And you can read out very detailed spectra from this particular device. So every night, this instrument is going to be sweeping the sky and collecting easily 30, 40, 50 terabytes of data. And you then stream the data to maybe a place like NERSC, where you do post-processing, you find out transient objects in the sky that were not there earlier, or you might be interested in other systematic shifts that might be happening in the sky. This is the Joint Genome Institute. So again, genomics as a discipline has become completely data-driven at this point in time. There are sequencers on the right, so the Illumina sequencer and some other sequencing technologies. So we at Berkeley Lab have the Joint Genome Institute in Walnut Creek, wherein they now have throughput capabilities to sequence the DNA for various specimens overnight. So the data is moved from the sequencer to NERSC, and then all of the processing pipelines around doing the cleaning, doing the sequencing, doing the assembly are all now run in a fairly routine throughput fashion. The challenge here being that doing, of course, throughput sequencing and assembly for individual DNA species, that's underway, but then the emerging challenges here are really around metagenomic assembly. So you might have a very complex ecosystem with many different species, and you got to figure out in one shot how many species there are and what their individual DNA sequence might be. So there is a host of interesting challenges there. Again, the world of science is known for creating exquisite instruments. The most elaborate, the most expensive at this point in time is the Large Hadron Collider. This instrument can produce data at a petabyte a second. And there is a host of pattern detectors coded up in FPGAs right next to the LHC, which are able to pick out, filter out uninteresting events, and then preserve or store interesting events that might be representative of new physics. The LHC is undergoing an upgrade right now, wherein they're actually going to be improving the quality of the light source and so on. And the amount of data now is going to be 10 times more than what has been the case historically. So again, these kinds of instruments are really all over in science, and the amount of data volumes coming in from these instruments is just enormous. So there's a aspect of volume and velocity and veracity that really pervades all of data-intensive science. So this is sort of my caricature again of some of the domains that you saw. And on the rows are really the kinds of problems. Given that you have these data sets coming in, there's a massive infrastructure challenge of how do you process it, how do you move it, how do you store it. But really the goal for you, the end goal is to analyze it so that you can learn some new science. And these are the kinds of analysis that are done. So you're probably interested in finding patterns in the new data. You're maybe interested in predicting some continuous valued quantity. So those are typically solved as supervised problems. And then you might have unsupervised problems in that you don't have a notion of a label. So you're interested in doing unsupervised clustering or dimensionality reduction. And then really learning new science, so where the anomalies might be. That's where a lot of the Nobel Prizes in high-G physics are. That's a key challenge. Now, there are many other domain sciences that are data-intensive in nature. There are many other problems you can solve. But sometimes it's useful to just think of it in a tabular format just to grasp what kinds of problems people are typically interested in solving. All right. So if I were to characterize what are the limitations of data analytics techniques as applied to these modern data-intensive science domains, I would say that right now, the way people proceed with solving classification problems or regression problems or clustering and so on and so forth is really largely based on heuristics. So domain scientists have tried to come up with heuristics, typically multivariate threshold conditions that are applied to either a native channel in the data or some derived quantity, some summary statistic, and then they're trying to threshold it and so on and so forth. And they feel that they have an intuition into how the data is and how clusters form, and then that's what they code up. And this is exactly what the FPGA detectors and the LHC do. There is a heuristic around energy deposits and so on, and then that's what they use to throw out uninteresting data. Now, some domains are a little more advanced than that, and they have certainly used classical statistical modeling to essentially capture properties of the data set and then use that for making decisions. Some of the domains are a little more advanced, and they use machine learning techniques like random forests or SVMs and so on and so forth. But I would say that I think to a very large extent, I think many of the domains are struggling with scaling these methods. So scaling classical statistical techniques or scaling heuristics and improving their accuracy to the large data sets that are now readily available. And I would say that traditional analytics as expressed in R are certainly struggling right now to scale on big HPC systems. So I think, again, going back to the talk that Stefan gave, I think there's a lot of promise right now in Python-centric frameworks, languages like Julia, and so on, to scale better on large HPC systems, and then also to scale the method to large data set. Now, of course, this is where deep learning really comes in. So I don't need to teach you about deep learning. You guys, at Google have really led the charge on development of methods, development of open frameworks. So thank you for, work on TensorFlow and so on. But really, I think I would say that collectively in science, we are really very excited about all of these developments in image recognition, image segmentation, the work on GANs and generating extremely realistic faces, control systems, both in self-driving cars and game-playing systems, and really many other developments. So really, I think an open question for us, having watched this maybe somewhat from the sidelines for the last 8 years or so, is how can deep learning impact these two broad ways in which we do science now: data analytics and computational modeling. So what I'm going to try to do next is walk you through a gallery of use cases wherein we've been systematically applying deep learning to these two kinds of problems. And I'm going to chat about what happens when you try to do that. What are the new issues that come up? So there's a nice blog post that we wrote about maybe 4 years now on how deep learning was being applied to many domain science problems. So I'm going to just mention a few. So in biology, for instance, we can look at noisy time series data. So there's a new device now called the Oxford Nanopore, not these big refrigerator sites, sequences, but something that can actually fit in a USB stick form factor. And it can look at a noisy time series, and essentially by plugging in LSTM models, we are now able to accurately predict ATCG sequences. Similarly, for ECOG data, we can apply fully connected networks to predict speech, or rather to predict syllables. We are getting to speech next. For high-energy physics experiments, instead of using ensemble Kalman filtering and so on, we are starting to explore essentially graph neural networks and stitch together space-time data to form tracks. Similarly, looking at uneven grids. So in this case, this is a grid for detecting neutrinos. This is the Eiffel Tower for scale, and this is a detector array that's underneath the ice of Antarctica. The grid is unevenly spaced. Particles stream through the universe, hit this detector array, and you got to be able to separate out the neutrinos, which are the interesting events, from uninteresting background stuff. So we are able to use graph neural networks again to be able to solve this classification problem. We're starting to use autoencoders for clustering events and so on. So really, I think we've been systematically exploring different kinds of architectures for solving data analytics problems in science. I want to maybe just dig into a little bit, one or two problems. So Jun Seok, who's on the call today, was involved in some of this work. This is close to my heart because I guess I recently completed a PhD in climate science from UC Berkeley. And one of the driving problems here is, I give you an image. It might be a satellite image. It might be a simulation output. And I'd like you to automatically find an extreme weather pattern in this image. So I'd like you to find where the tropical cyclones are, where the atmospheric rivers are, and so on. And I mentioned about heuristics. This is a very classical pictures that I've sketched out in the context of climate science. In that, while folks in computer vision, starting from the 70s, have explored a range of techniques, neural networks being one, but then also other classical machine learning techniques. And now they've certainly put together standardized data sets that have in many ways enabled the modern revolution of deep learning. Compare that to what has been done in climate science, in that all of these years, primarily what we've used are hand-tuned heuristics. And we really don't even have standardized data sets where you can compare different heuristics to. It's only now that some of these data sets are starting to come together. But really, there's just so much room for innovation in terms of solving pattern recognition problems in climate science, like the ones I just mentioned in this slide, but then also, similarly in other domain sciences. So again, comparing and contrasting what we need to do in climate science to what is done, by you in Google. Our images are spatiotemporal multivariate patches, and really we need to be able to say, given such a patch, is there a storm in this image? Localize the storm in a global image with many kinds of weather patterns. Draw variable size bounding boxes corresponding to different classes. And then the final problem is one of segmentation. So do a pixel level segmentation of where the storm system might be. And again, over the last 4 years, I would say that we've systematically adapted. I would say that we haven't really innovated a lot on the deep learning architecture per se, but we've successfully adapted many of the classical deep learning architectures and gotten them to work on climate data. So I just want to touch upon one particular example of segmentation, which is this last column here. So we can take DeepLab v3+ style architectures. The difference here being that we have 1 million pixels coming in with 16 channels, not RGB channels, but 16 channels corresponding to different physical variables. And then you have your usual encoder decoder piece with skip connections, and the output might be a million pixel image with 3 channels that correspond to a background class, which we don't care about, say a tropical cyclone and say an atmospheric river. So those are the predictions we want to make. Now, when you start operating on these large images that have many, many channels, you actually find that you require around 14 teraflops of computing to pass one image through the network. So that's a large amount of compute. And again, you might have a repository of, say, tens of thousands or hundreds of thousands of images, and that's just in one epoch of training. So really, when you think about doing training on this large data set, you really do need a very large machine. And this is sort of one of the reasons why we chose to run this training job as implemented in TensorFlow. So this is, sorry, I'll get to in a moment. But basically, we've been able to scale such architectures on large scientific data sets on tens of thousands of GPUs. So in this case, this was the Volta GPU from NVIDIA. And we've been able to achieve some really high performance numbers. So we've been able to scale this application in FP16 mode on the Tensor cores, on the Volta GPUs, and it's essentially hit an exaflop. So,
Prabhat, just a quick question on that model. Yeah. Does that whole model fit on a single GPU?
Yes. So in this case, we chose a model that so we did this project in 2018. We carefully chose the model that it would fit on a single GPU, so we didn't need to implement model parallelism. So this was purely a data parallel implementation. But this is a spatial model only, so it takes instantaneous images and produces instantaneous spatial predictions. We know that many of these storm systems evolve both in space and time. And once you start taking time into account, then the models will not fit on GPU at all.
Great.
Let me ask you about this whole thing, because this is it seems like an element of overall visualization, where before it was a giant pain to look at these, and like I'm thinking fire, which is I think the worst case scenario, where you just have all these flame licks moving around. You have to find reasonable common patterns for statistics.
Mm-hmm.
Because what are the challenges there? Just where you don't even know what a reasonable pattern is.
Yeah, so I guess your question is, how do we define what a tropical cyclone or what an atmospheric river is? Is that the question?
Right. And in the worst case, when you're trying to find these patterns in the data that you visually didn't know exist.
Yeah. So I think we'll point for the time being on the unknown patterns side of the story. So let's say we focus on patterns that we know about. So there are 2 ways, I guess, Greg. So one is, in this case, what we did, there's a subtle question around where did the 60,000 training images come from? And at that point in time, when we were doing this project in the circa 2018 timeframe, we just did not have ground truth data. So the best that we could do at this point in time was to take the best heuristic that the community seemed to agree around, code that up, and treat that as the ground truth, and see if our network could learn essentially a compact representation of what would make for a tropical cyclone, or what would make for an atmospheric river, or any other really climate pattern with known data. Now, subsequently, we have developed labeling interfaces for climate scientists to come in, load up a climate image on their browser, mark out where the pattern is, and then we have a QA/QC step wherein, after having crowdsourced this to 100 scientists around the globe, we try to normalize for quality of the labeling, throw away egregious outliers, so on and so forth. And then, we have now a ground truth data set wherein there is reasonable agreement on what visually makes for a pattern. So I think we have now a way to get at ground truth, having crowdsourced it to a select community. But really the challenge of, is there an unknown pattern, an anomaly that you haven't seen before? I would say that is still open. We have explored semi-supervised, so this is a purely supervised convolutional architecture. We have explored semi-supervised architectures wherein we throw in a reconstruction loss term and see how well that does. But I wouldn't say that the results are very conclusive at this point in time.
Okay.
So this is the output of such an architecture. So on the background is an image that just shows some flow. So you're looking at water vapor evolving. And then overlaid on that background in orange are where the tropical cyclones, the segmentation network thinks the tropical cyclones are. And in purple are contiguous long regions that correspond to atmospheric rivers. So again, some of you might have an atmospheric science background, others may not. But I think maybe you can take my word for it that the network seems to do a reasonably good job, even though this is a space-only model. it seems to do a reasonably good job of localizing and tracking stronger tropical cyclones. And then it does a reasonable job of tracking atmospheric rivers, so which are coherent structures of water vapor. There are certainly some errors that the network makes in that it fragments the atmospheric rivers a little more than we would like to. Whenever a tropical cyclone abuts or is next to an atmospheric river, there is some ambiguity there, which the network sometimes gets wrong. But overall, I would say that these are state-of-the-art results at this point in time. This is the best segmentation result that exists in climate science. Thanks to all of the training data that we've acquired, thanks to the large-scale runs that we've done, and a little bit of exploration that we've done on the architecture side. All right. So just one quick slide on the exascale achievement. So again, this is a big deal. Like, the simulation community has talked about exascale computing for about a decade now. And this was one of 2 applications that were able to successfully hit the billion floating point a second mark. So again, it was in FP16, not FP64. But still, such a large-scale job running on a compelling machine at Oak Ridge, hitting this mark. So this is the first AI application to get there. Was really quite satisfying. And this is a great collaboration between NERSC, NVIDIA, UC Berkeley, and Oak Ridge National Lab. I have to note that Rajat Monga was in the TensorFlow team at that point in time, and he and others in the TensorFlow team were really helpful. I mean, they supported us a lot in ensuring that TensorFlow was working well on GPUs and so on. So that was a great collaboration with Google as well. All right. So I think I'm running a little short on time. I just want to give you a flavor of a next analytics project, which is around a very sophisticated statistical model, which is basically a generative model. Essentially, in this project, what we're trying to do is to take all of the telescope data that exists in the world and infer a unified catalog of all stars and all galaxies. For about 2 years, we worked hand in hand with astronomers and physicists to develop, first principles generative model, in that we parameterize stars with a number of latent variables and galaxies with a mixture of Gaussians. And then we model out how an idealized galaxy or a star would result in a certain CCD, in a certain photon count on a CCD sensor. And I'll skip the details here, but basically we coded all of this up in Julia. We ran this inference procedure on a fairly large Sloan Digital Sky Survey dataset in about 15 minutes, and extracted the parameters corresponding to hundreds of millions of stellar objects. And again, this was the first Julia application to actually hit a petaflop in FP64 on a CPU-based system. And I think one of the interesting things from a modeling perspective that we learned along the way was that it turned out to be really hard to model galaxies with a mixture of Gaussians. So these are some pictures of galaxies that just show the remarkable visual diversity in how different galaxies look. And one of the things that we decided to do, after we just could not make any further progress with mixture of Gaussians in this project, was to really replace that piece of the generative model with an autoencoder. And once we did that, then we were able to capture the visual appearance of galaxies much better. So I think this is a lesson learned for us, in that conventional heuristics in analytics being replaced now by deep learning solutions. And then if you have worked very closely with a domain scientist on designing a graphical model, and your graphical model is just not cutting it because it does not have enough representative power, then selectively replacing some of the aspects of the graphical model with a suitable deep learning architecture is some of the things that are coming along. Now, the challenges that arise when you try to do that, I just presented 2 vignettes, but the challenges that arise when you try to do this in the analytics context is really around explainability. So I think very often when we show these state-of-the-art results to domain scientists, the very first question or the second question they have is, why did the deep learning system classify these pixels as belonging to a cyclone or what have you? And at that point, it's just not enough to say, oh, this is a deep convolutional architecture with skip connections and blah blah blah. I mean, those words don't make sense to scientists. So really, being able to explain succinctly why the deep learning system did what it did is turning out to be a challenge. A related problem of interpretability, in that if you want to explain what the features that the network is learning, you need to be able to explain it in terms of domain science semantics. So that, I think, is also an open challenge at this point in time. The issue we touched upon around lack of training data, we know that supervised architectures work best, but where does the training data come from? So that's really a sociological challenge related to different communities, and they just need to hopefully bootstrap the procedure for acquiring training data. I think many domain science communities, I think it's dawning on them now that supervised deep learning is working. It's only lack of training data that's holding them back. So really, I think encouraging the community to just come together and run hackathons wherein they collect training data, that I think is a challenge. I think I'm going to maybe just skim through the next set of issues, which is around how can deep learning be applied to computational models. So a few vignettes here. There are many, so I'm going to leave the slide with Greg, but you're welcome to obviously just check these links. I would say that for the last few years, we have explored how GANs as a model can provide a surrogate for a computationally expensive simulation. So some of the vignettes that we have are really around cosmology. So instead of running n-body simulations that track the evolution of dark matter in the universe, we have been able to train a DC GAN architecture, which can then synthesize virtual universes that seem to have identical statistical properties as compared to an n-body simulation. That was a very intriguing result 3 years ago. Similarly, particle physicists, eat up billions of core hours, CPU core hours around the world, carefully characterizing the behavior of their detectors. And I think we found out that you can also train GANs to be able to synthesize the behavior of a particle simulator in physics. It seems to work reasonably well. There is some intriguing line of work here by Max Jiang, who was actually doing an internship in Google Research some time back around overcoming the notion of a grid completely. So just think of a network predicting in continuous space-time a certain field. That field might be a flow, and imposing constraints on that flow. So that is an interesting work that's just come out. I would say that common to all of these projects is really how do we constrain the network, the neural network, to subscribe to some governing law, some constraints, some PD, some stochastic PD. So there is now a line of work around enforcing a statistical constraint or a PD constraint or a stochastic PD constraint that we are now starting to explore. So I'm going to skip maybe this slide. This is around generative models for high-energy physics. All of our diagnostic spectra around the real data sets and then also the fake spectra that we produce with the GAN seem to be lining up fairly well. This is something that we've seen for high-energy physics, but we've also seen this for the cosmology data set, so that's all intriguing. This particular project, this is in collaboration with George Kanandakis at Brown University, who, along with Mazia Raisi and others, are really doing some very innovative work on physics-informed deep learning, wherein they impose a term in the loss function that corresponds to the solution of your underlying PD or a stochastic PD. And last year, we worked with their team on using a stochastic PD to model subsurface flow for a site called the Hanford site. And once this network was suitably trained with some observation data and the stochastic PD constraint, we could ask the model to synthesize spatial fields that would hopefully subscribe to the stochastic PD constraint. Now, one of the interesting things here as well was that this was a GAN implemented in TensorFlow using Horvath that was again able to scale to 27,000 GPUs, and we were again able to exceed the exaflop mark. So this is probably one of the largest GANs that have been able to scale at that large larger computational resource.
So let me ask you about that one. I mean,
yes.
This seems like an example of scale bridging, where I'll give it another one where you want to say, given this climate simulation, what's the probability distribution of weather patterns that are consistent with this climate? Because if you want to do any model based on climate forecast, you need something like this. It seems like this is going to happen a lot, where you have models that are physics models that are too coarse, but you get much finer or just different predictions. So what's the state of that, and how reliable can you make these distributions?
Yeah, that's a great, that's an involved question, Brett. So, let me just say what we did in the context of this project. In some ways, the next slide will get to that. So in this case, what we ended up doing was, you really haven't heard of GANs that scale to batch sizes of tens of thousands. That's unheard of. So in this case, what we did for the problem was we spatially decomposed the problem. We asked some generators to make accurate predictions within the context of one spatial domain. And then we essentially set up other generators to operate across scale. So in some ways, we were hoping that this multi-scale decomposition of our spatial domain would force the collective set of generators to learn not just correlations within the context of one, within a certain spatial domain, but also across spatial domains. So that seemed to work okay for this problem. So that's what we did for this. But your question is actually more involved. And in this slide, maybe I'm just acknowledging that at least say in the context of a single climate simulation, not an ensemble of climate runs, but a single climate simulation. You may, as we've already acknowledged, your finest grid scale for a fixed spatial gridding technique, your finest grid scale might be a kilometer by kilometer or 25 by 25 kilometer box. And then the question is, what are you going to be doing about the subgrid scale processes? How are you going to be predicting those? And I guess I'm just acknowledging here that other people in the community, there are links here to other people's work, are looking at that exact problem in that while we might have used empirical histograms to make subgrid scale predictions, people are now starting to replace those empirical histograms with deep learning techniques that can be conditioned on whatever observational data you might have in that grid. So that is something that people are definitely looking at. Your original question, Greg, is much more involved. I think I'll need to think about that some more. So I think maybe that really is around how do you design an ensemble to track different modes in the climate system more accurately. That's a harder problem that I don't think many people are looking at right now. Does that make sense, Greg?
Oh yeah, thank you.
Sure. All right. So I think having breezed through some of the DL applications for computation modeling, I think the open challenges that have now emerged are really, basically you're trying to appease a community, the applied math community in particular, that has been in existence for 40 years. So I would say that the bar that they have is really quite high. And I think the pushback that we get from them is really around the lack of theory or the perceived lack of theory in deep learning. So the kinds of concerns that they have are really around, what can you prove to me about this deep learning augmented model? What can you say about generalization limits? What can you tell me about how much training data do I really need to provide? What can you tell me about when and where the model is going to fail? And really, formal proofs of robustness are really quite important for that community. So that is something I would just like to convey maybe in this meeting, that's a challenge that I perceive is going to be a barrier in terms of successfully incorporating deep learning in well-established computation models. Now, certainly some ideas that are floating around really are around baking in domain knowledge. So you can customize loss terms. You can maybe even come up with architectures that can encode in physics. So those are all ideas that are being explored. I think we are starting, just as on the deep learning side in Google, there are issues that come up regarding inference. Some of the early TPU architectures were really targeted at inference. I think we are starting to see now, as people are starting to plug in a deep learning inference module in their PDE solver, I think people are starting to think about or grapple with what might be some software engineering issues that come up. And then, from a production stability perspective, they really don't want the behavior of the simulation to diverge over time. So that's an issue that is starting to come up. So imagine that you have a climate code written in Fortran 77, and now you have this new, Python-based deep learning framework. How are you going to interface those two cleanly? I think the one key thought, the reason I actually last night took some time to sketch out this protocol, we in the applied math community, we have a nice protocol for when to apply computational modeling. If you think about the protocol for deep learning, it's fairly simplistic. It says throw more data at the problem or throw a more complex network at the problem. And that seems very naive compared to the sophistication of the protocol that we use in computational modeling. So I think as we try to convince computational modelers to adopt deep learning, I think our protocol in deep learning has to become a little more sophisticated, maybe even start approaching the workflow on the right. All right, so just some concluding thoughts. So places like NERSC, supercomputing centers like NERSC have been doing computational modeling, and this computational modeling has driven scientific discovery for 40 years. Frankly, this is still the incumbent. That is probably the primary way in which science will continue to get done. There are some known limitations in approaching science this way. I think I commented on many of these problems earlier. On the data-intensive science, I would say that in the last decade, the trend has become really clear that many domains are going to be data-driven in nature, and the challenges are around use of heuristics, limited scaling of conventional heuristics or statistical techniques to large data sets and computational scale. Deep learning, obviously we're happy to acknowledge that this revolution has really been led by the industry. I would say that domain sciences are 5 to 6 years late, but they're catching up slowly. We are seeing, I think, across the board, state-of-the-art results in analytics, hybrid models that marry, I guess, conventional statistics with deep learning. I think they're starting to emerge now. On the deep learning applied to computational side, I think people are still struggling with exactly what the value proposition is. I think we can see a value proposition in terms of acceleration of our codes. So it's possible that some of the conventional codes which are struggling to scale can be sped up by a factor of 3, 5, or sometimes 2 to 3 orders of magnitude. So I think we can see that value proposition. I think we can also see a value proposition for once you, in a data-driven way, train your model, we can see that the model can probably do a better job at interpolating a vast configuration space. So I think that is something we can see happening. I think there's a speculation in the community that the kinds of control problems that Google and others, I mean, you all have succeeded in. I think those kinds of techniques could be retargeted for exploring large parameter spaces. So there's a speculation, but I think we need to test that out. But as I cautioned, I think while we are starting to see a deluge of papers in Nature, Science, PNAS, other domain journals, I do think that there will be a barrier, an activation barrier in adopting many of these techniques till the theoretical foundations really fall into place. So hopefully, I think from this talk, you have a sense that there are a number of opportunities for us to collaborate. There are science applications where we can work together. There's certainly underlying theory, new deep learning architectures that can be developed. On the tool software side, we've certainly pushed very hard on TensorFlow, on our stack. But certainly, I think many of the lessons learned around scaling these applications to tens of thousands of GPUs, tens of thousands of CPUs, that's something we know now. And I think there's natural synergy there in terms of collaboration. All right, so thanks very much. So Greg, I'm sorry I ran a little over than I planned, but happy to take any questions now.
Hi, Prabhat.
Hi.
So you mentioned AI is a little bit lacking on the theory side. So I've heard DARPA has an explainable AI project started about a few years ago. Have you been in contact with them, and what's the progress?
Yes. So if I had to rank order federal agencies, yes, DARPA has certainly led the charge on explainable AI. NSF is now catching up. And the DOE, I think, has been a little slow to really put funding, but we are hoping that they will hopefully soon launch a decadal program on AI for science. So I think we're hoping some movement in that space. So yes, I think, Panpan, we are tracking some of the work that's been done in that space. Frankly, I think we are struggling to adapt even some of the tools that Google has put out with regards to visualization of trained networks. And they don't seem to be working out of the box. So of course, there's a little bit of customization that needs to happen in terms of ingesting scientific data. But this issue of attaching semantic meaning to the output of a visualization tool or some explainable tool, there's a very heavy bias of these tools towards visual RGB data. And I think we are struggling right now in adapting some of these tools that are coming out of the explainable AI project in DARPA, or even from Google, to our context. So maybe it's just a matter of time before these tools are general enough that they can actually work across the data that we care about or the kinds of problems that we care about. But it's early days. I mean, I think these programs have really only existed for 2 or 3 years now. So it just takes time for truly general pieces of software artifacts to come up. So the answer is, I think we're tracking it politely, but I think we're hoping that these tools will become more useful in the future.
Got it. Thank you.
Sure.
And very great talk.
Good to see you.
Nice to see you too.
Well, let me ask a broader question. It's not something DOE normally does, but where simulation style stuff and data, ML type stuff, it seems to be both useful is in social modeling human systems where there are no governing laws. You have to discover them, but then you have to forecast them. And in DOE, probably discrete event simulation is probably where that's actually done. I guess what's been your experience or opinions about that particular marriage?
The marriage of what? Like combining simulations and data modeling?
And data modeling for social or just discrete event things without an underlying theory.
Sure. Yes, I think typically, the DOE has shied away from, social networking data sets. I would say that the application context in which this is coming up is towards transport modeling. So essentially, you might have traffic patterns in a city that are changing with time, and you want to maybe design a smarter grid or smarter traffic infrastructure. So, I think we're starting to plug in some discrete event simulators in that context and seeing if they do a good job in explaining the observational data that we have. As people who are trying to parallelize and optimize COVID disease, epidemiological models, I guess are finding such discrete event simulators don't really scale very well. So that's, I think, a common challenge. So anyways, I would say that there are, first order set of problems around getting such models to run well on a single node and then hopefully scale to multiple nodes. So there are some HPC challenges that have certainly come about. But I would say that, Greg, I think, with regards to a richer set of problems around social modeling, I think we're just not doing enough there. As several of Penpon, you're on the call. Kathy and others, they've done a lot of work on, Kathy Ellick and others have done a lot of work on graph analytics and modeling graphs with sparse matrices and so on and so forth. But we've really found very, very few killer applications for graphs in science. You would have thought that, of course, social modeling and so on, I mean, that's naturally amenable towards graph modeling and application of sparse linear algebra. But we just don't see to see that very often in the DOE. But that's just an artifact of the DOE, I would say. Does that make sense?
Yeah, actually, when you're pushing the graphs, I'm actually thinking about graph neural networks as being, I'm thinking modeling the whole economy or something like this, where you have like a graph of interacting cities, zip codes, individuals, I mean, in the thing, in the farthest domain. But if you have time series for a lot of these units, where if you did model them as a graph with, the way this works is you just propagate messages around, then you have to backdrop back through the graph. It seems like that's a supercomputing problem, but certainly nothing I've ever heard of.
Yep. Yeah, you could. I think right now there are some analogs in science wherein you are maybe looking at macromolecular structures and how they might deform in the subsurface. And you could represent each macromolecular structure by a node in the graph and then see either how the topology of the graph might evolve over time or how the collective properties of that graph might change. So I think there are some problems like that we are starting to see. I wouldn't say that, again, graph neural networks are at the frontier of in deep learning as well. So to the extent that scientists are slowly adopting simple convolutional architectures, augmenting simple convolutional architectures with some sequence through LSTMs or what have you, I think they are only now starting to move towards graph neural networks. So not there yet, but we'll see how that changes.
Okay, that makes sense. Yeah, thank you. This was fascinating and covered a whole lot of topics.
Okay, sounds good.